Good morning. Let's go ahead and get started. So we're going to be looking at chapter 1 today. It's going to focus on measurement and kind of giving an overview of physics and science in general. On each one of these chapters, what we're going to have at the beginning are a list of the topics that are in that particular chapter. I'm gonna tend to go through those quickly. Those are more for your reference when you're going back through the notes for the course. I got the textbook here. Textbook is ready to go. We have our course mascot. We have Laney the Eagle here with us. So let's go ahead and get started with chapter 1. We're going to start by taking a look at science. What kind of characterizes science? What makes science science? And science is observation based. So the important first step towards any scientific theory requires looking at observations and trying to find if there's some kind of pattern going on. Is there something going on in the way that nature is working, or in the way that the universe is working? And then we have theories that are created to I don't know if it's so much explain observations, in many cases just kind of come up with something that would describe how nature works. Now, the important thing in science with the theories is that the idea is that they'll make predictions. So once we say, oh, nature works this way, that means that if we try this, something particular should happen from that. And then observations enable us to go back and check and see if the prediction is reliable. Now, no theory, this is an important point here, I guess, no theory can be absolutely verified because you have to make an infinite number of observations. But a theory can be sort of disproven, or it can be shown to have fallen out of usefulness if we find that the observations don't match with the predictions. How do new theories get accepted in science? Predictions that agree better with the data and explain a wider range of phenomenon. Now here, they always, Aristotle always gets brought up. Aristotle apparently said that objects prefer being at rest, and left to themselves, objects will slow down and stop. Galileo, though, recognized from observations that objects tend to stay in motion unless acted upon by some kind of a force. So the Galileo approach turns out that this prediction, when we go and do a series of observations, turns out actually to be the case. All right. Principles of physics just show up all over. So here are some kind of engineering applications, but it's not just engineering. It's the biological sciences, all throughout chemistry. How do we understand how chemical reactions take place? So physics just shows up everywhere. Physics is kind of a foundational science that if we ask enough questions about something, eventually we're going to be asking questions related to physics. Now within physics, we have models, theories, laws. These are just different names for different ideas within physics that we've come up with that explain or describe, in some cases, just describe how what we're observing. And so models are pretty much, we use these all the time, but the models themselves often have built-in limitations. So when we say this is a model we're using right now, it's usually the idea it's not based on anything fundamental. It's just some kind of a formula, some kind of a description we've come up with that works well in certain circumstances. A theory, we tend to reserve the word theory for something that has more detail to it and makes more specific types of predictions. Now it says here that a law is a brief description of how nature behaves. you know, I think the word law has been replaced by the word theory. If you go back to the 1800s, you know, the laws of motion, the laws of thermodynamics, and then when we come into the 1900s, then we start saying, the theory of special relativity, or quantum theory. So it's just kind of a, not necessarily generational, but just over different periods of time, we've shifted over more towards using the word theory. Now, I'm not so worried about all that stuff. You know, all of that stuff that we looked at on those earlier slides, it really just kind of comes down to we make observations, and then we come up with theories or models of what's going on, and then we go and make more observations, and it's just a back and forth thing. You know, what makes science so powerful is that at the end of the day, if you come up with some ideas, and you go out and you check all the observations that you can make on those, if you find out that the theories you came up with don't predict the observations, then you can toss out the theory. Okay? And so what makes science powerful, I think, is this ability to put aside something that just proves not to be very reliable at describing how nature works. Now, that said, there are certainly theories and laws within physics that we're going to use in this course, which we know they have certain limitations. A good portion of this course is going to be based on what we call Newton's laws of motion, and it's Newton's description of gravity. And we know that there's a better description now. We know that in 1915, Einstein came up with general relativity, and that's a better description of motion, and it's a better description of gravity. But it turns out it's like, you know, 1 trillion times harder to work with than Newton's description. And so we still use Newton's description. We feel like we have a good handle on where the limitations are. And so we prefer working in a very useful description of how motion works, of how forces operate, of what energy is. And it works for us really well. And again, we kind of know where the limitations are, so when we get close to those, we can point those out. Now, let's get back to doing some measurements. So the statement here, no measurement is exact. There's always a little bit of what we call uncertainty in a measurement. So whether it's the biological sciences, or the physical sciences, or medical sciences, or whatever, engineering, what we're going to be doing is making some kind of measurements. Now, when I look at that measurement right there, I can't really tell if they've got that edge flush or not, but it looks to me like 8.8 centimeters, I guess is what those are. So those are centimeters, and it would be difficult to measure the... So it's saying that given the board that we're taking a look at, this 2x4 or whatever, that it would be difficult to measure this with an accuracy of more than plus or minus 1 millimeter. So that gives us an idea of how much uncertainty there is in this particular measurement. Now, the board itself may have a variation in its width of more than 1 millimeter. So in some cases, some measurement that we're making may have that uncertainty just built right into it from the start. Now, what we could do then is we could take this uncertainty, let's say that it's 8.8 is what they came up with. Oh, they came up right at 8.8. So 8.8 centimeters plus or minus 0.1. Let's say that we did that measurement, and best we could tell, it came right on the 8.8, but we're still saying, I could still be off by a millimeter. And so a tenth of a centimeter is a millimeter. What that leads us to, this is the uncertainty itself. Okay. Now, I should say this while we're going through these measurement discussion, that when we're doing homework problems, you want to be thinking in terms of uncertainties all the time, and especially when we're doing labs. So in lab, pretty much every measurement that we make, we want to be able to put some kind of an uncertainty value on that. And we want to be able to keep track of that through the lab exercises that we're going to be working on. So for this particular measurement, it was 8.8 plus or minus 0.1 centimeters. And what we can do from that is we can introduce this idea of relative uncertainty. Now this is really useful. They're both useful, the uncertainty itself and then the relative uncertainty. Now they're calling it percent uncertainty. I think I'm going to refer to it as relative uncertainty. And what you do is you take the uncertainty amount and divide that through by the measurement itself. And in many cases, this is just really, really useful to give us an idea of what level of accuracy we're maintaining. What we can do is we can take this measurement, which had units of centimeters, and now what we've done is we've eliminated the units. The centimeters cancel out, and when we multiply by 100, what we're finding is that this works out to be about 1%. So what that says is this particular measurement is accurate probably to within 1%. Now if I've got a whole series of measurements that I'm making, maybe one of them is accurate to 1% and another one's accurate to 2%, and if there's one that's only accurate to 10%, well then the 1 and the 2's don't sound very consequential anymore. So what we can do by listing relative uncertainties of all the measurements that we're making, what we can do is we can identify where the major sources of uncertainty are for a particular set of measurements and for a calculation of some sort. Okay, so I wrote in, you could imagine putting in 1.1. You seldom want more than 2 significant figures. Usually, well, in most cases, we probably want to have, for lab reports and stuff, we want to be able to have relative uncertainties to 2 significant figures. Now let's talk about significant figures a bit. The number of significant figures in a number is the number of reliably known digits. And so, coming back to this, in this measurement, we have 2 digits that are meaningful. But if I wanted to put a 3rd digit in there, I really wouldn't know necessarily what that would be. What should I put in as a 3rd measurement, given the limitations of the measurement I was making? Now, to some extent, these are judgment calls. And so often, students have a little difficulty in going, yeah, but how do I determine the uncertainties? So take a look at the measuring device. And use the measuring device as best you can. Understand how the measuring device is supposed to be used, and then use your best judgment. I still think that looks like 8.8. Oh no, maybe there's a little parallax. It's already 8.81 or 2, right? Okay. Now, one thing I should also point out is significant figures are going to be important, but we're not going to obsess over them. Okay, so let's take a look at a couple of examples they have here. So if someone reports the number 23.21 centimeters, that's telling the reader that they reliably were able to get down and make an estimate on that last digit. So that's being measured down to hundredths of centimeters or tenths of millimeters. Now, a centimeter is like that, right? And so you want to get familiar with these units. So when these units come up, you always want to pause for a minute, especially in the early part of a course. Build those habits of going, yeah, I can kind of visualize what a centimeter would look like. And so 23.21, we're looking at something, 20 centimeters is going to be like this. And they're claiming something like this is being measured down to the level of a hundredth of a centimeter. So it was some kind of a precision instrument that would have been necessary to make that measurement. Now this is 4 significant figures. We start here and we count 1, 2, 3, 4. Notice this is one of the places where we start running into trouble. So when we have a decimal with zeros after it, those zeros really aren't meaningful digits. The 6 and the 2 tell us something, but the 0 is really there just because we're working in terms of centimeters. So the zeros to the left don't tell us anything about the measurement. Now zeros to the right, if there were a 0 over on this side, that would mean that it was measured to be 620. That one would tell us something. So zeros on the left don't count, zeros on the right do. This number has only 2 significant figures. Now I'm going to say this up front, like 99% of the work that we do in the course is going to be at the level of 3 significant figures. And that's because most of the measuring devices we work with have been designed to try and measure things accurate to about 1% or better. And that means that 3 significant figures are entirely enough. They're adequate. Now, we don't want to round back. You know, I'm always concerned that students are so cautious with significant figures that sometimes they round back more than is needed in a particular problem. And so this is one of the times when I see it a lot in lab reports, 0.062, and I go, well, where's the third significant figure? Couldn't we get a third one? We would like to have 3 significance everywhere on all of our numbers, if possible. So again, the initial zeros don't count, so you start counting here. So if you're measuring something, you should try for that third significant figure. Now, the number 80 kilometers, that's ambiguous because we don't know if it was measured right to 80 kilometers, you know, right to the kilometer, or whether it's just kind of an estimate. 80, 90 kilometers, maybe 80. So the way you can make that specific is to put a decimal after the 0. Okay. Well, we'll have more to say about this in the lab reports and when we start looking at some examples. So I'm going to say don't start thinking about it. Start thinking about the significant figures. When multiplying or dividing numbers together, the number of significant figures in the answer should be used in the calculation with the fewest significant figures. So let's see, let's take these numbers right here. 11.3 centimeters times 6.8 centimeters gives us 77 centimeters. Okay, so we know that there's only 2 significant figures here, there are 3 here, so the answer itself is only going to be accurate probably to 2 significant figures. Now, I'm not going to worry if you keep 1 extra significant figure. You know, when I was in research, it was very common. People always wanted to know what that next number was, just to kind of gauge things. The important thing is for you to realize that if this is only at 2 significant figures, then let's say I'm looking at this number over here, 76.8, I really know that there's only really 2 significant figures that are going to be very reliable with this. But again, a lot of times people just want to know, what was the number, what was the next number? And then once you're past this, it's probably not that useful. When adding or subtracting, you line everything up and keep track of the columns. Okay, and another thing to realize is that the significant figures is not a completely reliable method. You know, the better method here is to work from the percent uncertainties or the relative uncertainties. All right, here's an issue is calculators. So here's a calculator. They're saying that what happened here is someone took the number 2.0. Okay, so they're saying someone actually put in 2.0 and divided by 3.0. Those were the numbers. And then this is what shows up in the calculator is 0.6666666667. And in this case, the calculator is giving me too many significant figures. Now, there are calculators out there that will, you can set the number of significant figures. I believe my calculator does that, and it's not a recent calculator. But for this, you would need to know to count, you know, to round back to 2, or again, I'm not going to worry if you keep an extra significant figure. Certainly in the calculations, that's fine. The bottom calculator, we took 2.5 multiplied by 3.2, and here the calculator just gave 8, but it didn't respond with the zeros. Okay, so that's another problem with many calculators, is they don't keep track of the significant figures. So you would need to add that 0 on. You would need to add on a 0 or 2 to show that when these numbers were multiplied, the number was actually 8.0 or 8.00. All right, here's another example with making measurements and deciding how many digits should we keep for that particular measurement. So this is using a protractor, and you're measuring an angle that is at 30 degrees. Now, this is coming in at 30. So here is the 30 degrees. It looks like it might be just a bit under 30 degrees. How many significant figures should you quote? I would say with this protractor, you really should be able to get down to, now here's 29 degrees, there is 30. You should be able to estimate tenths of a degree. And we often are going to be doing that in lab. So what we will do is we'll take, a measuring device like a protractor or the ruler that we saw earlier, and it will have markings on it, and you can look at those 2 markings, and then you can report your best estimate between those 2 markings. Now, you're not going to be able to do much better than 1 digit beyond those markings. So for this, I think tenths of a degree are probably the most sensible way to report the number. If there's ever a question on any of that, just let me know. Just ask, and we can take a look at it together and think about how we would do that measurement. So let's take a look at a couple of numerical examples here. So here's one that kind of extended from that previous slide. Let's say that we do the measurement and we decide that we've measured it right at 30 degrees plus or minus 0.1. But if, someone else comes in and goes, I'm not sure about it. I'm not really thinking I can reliably measure this to a tenth of a degree. Maybe I'm going to list this as plus or minus 2/10 of a degree. And then someone else comes in and goes, I'm not even sure about the way the protractor has been manufactured. And so I'm going to put in 30 degrees plus or minus a half degree. I'm going to be more conservative and allow for a larger uncertainty. And that's fine. And again, this is going to be based on kind of a judgment that you're going to have to make. Well, let's take a look and see what the relative uncertainties would be for these. This would be a tenth, for the student that has decided, I'm going to use plus or minus a tenth, divided by 30. That would work out to be, the fraction here would work out to be 0.0033, or the decimal. And then if I multiply by 100, that says that this measurement then would have a relative uncertainty of 1/3%. Now for the student that decided, no, I want to use 0.2 plus or minus, that works out to 0.67%. And then for the student that has decided, I'm going to be really cautious and say that there might be an uncertainty as large as a half a degree. And that worked out to be 0.0167, which in percentages I ended up writing as 1.7. Okay, so this is based somewhat on the judgment of how reliable do you think that measuring device was. Now, in a formula, let's say we measure this angle, but the angle is not used directly. Instead, it's plugged into a formula that has a cosine or a sine function. Well, the cosine of the sine function will have an effect on the uncertainty of that number. So for example, if I take the cosine of 30, that comes in at 0.8660, but let's say that we're off by a half a degree. So I'm going to use this most conservative uncertainty estimate. And that's saying that, well, maybe it's not 30, maybe it's as low as 29.5, or maybe it's as large as 30.5. I'm just not sure with the protractor. Well, that would say that in my formula, my cosine formula of the angle, the numbers could vary between 0.8660 and it can vary between 0.8704 and 0.8616. Sorry, this was the central one. These are the extreme values. So it's going to come in somewhere between here. Well, we could do a percent uncertainty of the cosine of theta. And so for the cosine of theta, what we could do is take a look at these two numbers and say they represent an increase or a decrease of 0.0044 compared with the central value. This number is larger by 0.0044. This number is smaller by 0.044. So I can do the plus or minus thing here, divide through by that central value. That gives me a relative uncertainty of 0.0051, which is 0.51%. Okay, so that's saying if I take the cosine of the angle, now let's see, the angle itself has an uncertainty, a relative uncertainty of 1.7%, but if I take the cosine of that angle, the relative uncertainty is only 0.5%. Okay, so some of these functions are going to change the level of uncertainty we have in a particular problem. If I do the very same thing using the sine, so I'm going to take the sine of 30, which is 1/2, and then the sine of 29.5, and then the sine of 30.5, and, just for comparison. So what I find here is that if I'm looking at an angle of 30 degrees, the cosine is not so sensitive to variations in the angle, but the sine function is more so. So what I'm finding is the sine function in and around 30 degrees with a 1/2 degree uncertainty, we're getting 1.50% difference. Relative uncertainty. So the angle itself, again, quick review here, the angle itself came in at 1.67 or 1.7%. The cosine of the angle only had a 0.5% difference, and then the sine of that angle had an uncertainty of 1.5. All right. Now, what about significant figures? Let's take a look at the significant figures too. Let's say that we have a number, 11.7, and we have another number that's 95.4. Now, if I don't do the plus or minus stuff, so I'm going to ignore that right now, I'm going to look at that and say, how many significant figures is that? You go 3, and how many significant figures is 95.4? Well, that one's also 3 significant figures. Now, you might think that this suggests that the relative uncertainty would be the same for those two numbers, but it's not. If we're going to report the uncertainty as plus or minus 0.1, and here as plus or minus 0.1, and then carry out the relative uncertainty calculation, this number ends up with a relative uncertainty of 0.85%, but this number is only a relative uncertainty of 0.10. Okay, so again, what was on that previous slide saying that, significant figures aren't, they're just kind of an estimate as to how much reliability we're going to have in a number. You really want to use these relative uncertainties. You really want to be able to estimate these plus or minuses and how much in order to come up with relative uncertainties. These are going to be more reliable. Now in homework problems, there aren't going to be the plus or minuses typically. And so this isn't going to become an issue, but in lab reports it will. All right, so both of those numbers were 3 significant figures. I wrote them twice. Both of those are 3 significant figures, but they have very different relative uncertainties. Just something to be aware of. Okay, what about scientific notation? Scientific notation is commonly used in physics, and scientific notation is handy because we can very clearly show level of precision with scientific notation. So let's say that we have a number, 36,900, that's ambiguous. We're not sure how many significant figures there are there. We're thinking at least the 3, 6, and the 9 are meaningful, but we're not sure if things were measured to the level of these zeros or not. Now, if we use scientific notation, 36,900 could be written as 3.69 10 to the fourth. And then we go, oh, that's three significant figures. That's 3 digits of precision with which this number is being measured. But notice, if we write it as 3.690, well, that lets people know that we actually measured the zero. At least the first one got measured. So that would be 4 significant figures. So scientific notation is really handy in that it allows us to be more precise about the level of precision that we have. Now, much of physics does involve approximation, and those also are going to come into play. So when we get into lab, we'll find that there are idealizations that we're making in some cases, or approximations. So these are all things that, we learn to work with. And so it's good to start thinking about all of these issues. Okay, so there's always this issue of accuracy versus precision. Now, this is interesting. It says accuracy is how close a measurement has come to the true value. Now, the problem in science is no one knows what the true value is. That's why we continue to do measurements. We try and get more and more reliable measurements of different things. What's the density of copper, or what's what's the pressure in a at a certain level within a fluid. So we're always trying to find out what what's the speed of light, what the true value is, but no one ever has, okay, this is it, this is the true value. It's this number right here. So, and I know that this is one of my biggest concerns, I guess, in science classes, is that I find a lot of times that students have, and possibly from other science classes you've taken, students are rewarded for getting the true value or the right value. And actually, that's not how science works at all. Science says that you go in, you do the measurements as carefully as you can, you follow through with all the calculations, you double check all the numbers, you make your way through, and then whatever you end up with, you present that as your results. You're not trying to get a particular number. A lot of times in lab reports, students will go, the lab was successful because we got the number that we wanted to get. You go, no, that's not it. That's not science. So science, we do the measurements very carefully, we do the calculations very carefully, and then we take a look at what numbers we ended up with. If we see that there's something that probably doesn't make sense, we go back and double check. All right? But we're not trying to get any particular value. So the idea is with the true value, no one knows what the true value is. So that means that we can have an idea of what our accuracy is, but we're never going to know for sure how accurate our numbers are. There's a lot of things that can tell us or suggest to us that the numbers are reliable or that they're accurate. Okay, so precision has to do with, now here it says the repeatability of the measurement. So, yeah, and so precision to me is kind of, yeah, we could say that. I mean, the reliability of being able to reproduce that same measurement using the same instrument. Now here, it says, is it possible to be accurate without being precise? And you go, yeah, I could do a series of measurements, and maybe the measurements I get numbers all over the place, but when I do the average comes in very close to what we consider to be an accepted value. So it's possible that by averaging over some number of measurements that we end up with something reliable. Or it could be that even though we're not being very careful with any of the instruments, just by being lucky, we end up with a number that is a reliable value. Okay, let's get into units. So this is going to be really important to us. Everything every physical quantity that we define is going to have units attached to it, more or less. And so let's take a look and see what kind of measurements we want to be able to make. We want to be able to measure lengths. And the standard units for lengths are meters. Now, over here it says what's the standard this is used, what's this determined by. And the meter actually now is determined in terms of speed of light measurements. So that's not such an important concern for us. What we're mostly interested in is when you read the word meter or you hear it, you immediately go, oh, that's a meter. Meter looks like that. I know how big a meter is. You want to really integrate an idea of what a meter looks like. What that means is if you get, let's say you're doing a homework problem or there's a problem on a midterm or something, and you get an answer, and you want to be able to look at that number and the units attached to it and say, boy, does that make sense? You know, if you're calculating how fast a car is going and the car turns out to be going, you know, 1,000,000 kilometers a second, you have to wonder if maybe something went wrong in the calculations. So by looking at units and knowing what they mean and looking at the numbers, you're able to catch possible errors that have come up. So anyway, the meter is what we're going to be using. Seconds, time is going to get measured in seconds. Is that still the cesium vibrations? I'm not sure if, maybe so. The mass is measured in kilograms. Now the slides here were old enough that they had listed a platinum cylinder stored in the International Bureau of Weights and Measures in Paris was the official kilogram. And I don't know if you guys know the story about this, but it's been ongoing over the past several years, that the standard kilogram that people have been storing has proven not to be very reliable. When they bring it out and measure it against other standard kilograms, it doesn't agree. And so anyway, we've moved on. The kilogram is now measured in terms of something we call Planck's constant, and Planck's constant can be measured very reliably. So we don't have an object that determines the kilogram anymore. It's determined in terms of this measurement of a fundamental constant. Okay, and again, we're not so concerned about how the standards are maintained, which is important, and if you're interested, that's excellent. But we're mostly, again, getting a feel for what's a meter, what's a second, what's a kilogram. Now, a kilogram of water is a liter. So if you have a liter of water and you lift up a liter bottle of water, that's about that's the mass roughly of 1 kilogram. Okay, and then for these units that we're looking at here in the textbook, they've got these tables. These are kind of interesting, I guess. In terms of lengths, what are the smallest kind of things we've ever measured? And neutrons and protons can be pretty tiny, 10 to the minus 15 meters. Okay, so you can imagine that's a really, really tiny measurement. Now, let's see, what things can we see? Oh, a sheet of paper is actually coming in at about 1/10 of a millimeter. And that's about what we can see. We can see reliably down to 1/10, maybe down to several hundredths of a millimeter of the thinnest things. When it gets thinner than that, our vision doesn't have the resolution to discern those individual objects. So we're actually able to see maybe out to this range. We don't see viruses directly. We need instrumentation to help us with that. Same thing with atoms and neutrons and protons. We need some kind of instrumentation. It's a nice picture of those viruses, right, on that larger cell over here with their DNA inside the virus. Let's see, how large can things get? And here it is saying, in terms of length, and here it is saying the distance to the most distant galaxies we've observed, 10 to the 26. So, if we combine all that, 10 to the 15, that's like 40 orders of magnitude difference between those. Okay, so a wide range of length that we might run into in the course. What about times? one of the shortest time intervals that we've measured, and that's the lifetime of very unstable particles. So we have measured down to 10 to the minus 23 seconds. We believe the age of the universe. Now, when we say age of the universe, what we really mean, I think, we have to be clear about that. There was an early phase of the universe. There was a high temperature, high density phase we have evidence for that the universe went through, and we date things from that time. And as you guys know, that high density, high temperature state was called the Big Bang. It's not a very good, it was a plasma. So plasma was everywhere in the universe, and I think, how does that theme song go? The whole universe was in a hot, dense state. Then 14 billion years ago, right? And so they got it right. The whole universe was plasma at that time. So it wasn't like there was some plasma concentrated here and then it blew up or something. It's like the whole universe was filled with plasma. Anyway, we can talk more about that later, about what expansion of space means. But let's move on here for now. What range of masses do we work with? Electrons are really low mass. They're about 10 to the minus 30 kilograms. An entire galaxy is at about 10 to the 41. So here we've got 70 orders of magnitude. Okay, so, you know, mass is an important something to be measuring. There's all these prefixes, and the prefixes are really handy. So I encourage you to make use of some of these prefixes, or prefixes. The ones that do get used are kilo, mega, giga, tera, and peta's not going to come up that often for us, but these other ones will from time to time. You guys know what kilometers are, right? So a kilometer is 1,000 meters. What's a kilogram? It's 1,000 grams. And so by using these prefixes, we can simplify the numbering that we have to use. Now, again, the ones that are used most commonly for large amounts, 10 to the third, mega is 1,000,000, giga is 1,000,000,000, and tera is 1,000,000,000,000. Fortunately, storage devices on computers have, I hope, familiarized all of you with megas and gigas and teras, right, and kilos. Let's see, hecto does not get used very often, deca doesn't. Deci gets used occasionally, I didn't highlight it. Centi gets used in centimeters. So there's the big exception here is centimeters. Centimeters are so handy. We're going to be using centimeters all the time in homework problems, centimeters all the time in lab. So centimeters you want to be familiar with. So what's a meter? That's a meter, right? And what's a centimeter? Well, it's 100th, and that turns out to be that big. What's a millimeter? And a millimeter is a 1,000th of a meter, and so it's smaller. All right, and you should think in those terms when you look at something. So in lab, it's very common, you know, a student or a group of students will come up and they'll show me an object and they go, well, we measure, you know, an object that's, you know, this size. And they'll go, yeah, we measured that to be 2 millimeters. And I go, are you sure millimeters, maybe centimeters instead? So pay attention to the units and practice using them and thinking about them. Now, milli gets used all the time. Micro, nano, pico, and femto, those are the other powers of 1,000. 10 to the minus 3, minus 6, minus 9, minus 12, minus 15. Certainly by the time we're through the whole year, physics, you know, 3A and 3B combined. We will make use of all of those. Okay, so the prefixes are great. Practice using those. Now, in terms of units, how many units are out there? Well, we have length, which are in meters, and time, which is in seconds, and mass, which is, for us, we're going to be using kilograms, not grams. Kilograms turn out to be in most applications for physics and well, we're going to be using kilograms, let's just say that. So I know that in chemistry they tend to use centimeters, seconds, and grams instead, but these are going to be the standard units for us. Now, what other units do we have to introduce? Throughout the entire year, there's only a handful of other units that are going to come up. One of those is going to be, this is saying the ampere, that's a measurement of electric current. But actually, instead of that, I'm going to say the fundamental unit here is the coulomb. It's a measure of electric magnetic charge. So we need something that tells us about electric and magnetic charge. Temperature is Kelvin. That's an absolute temperature. The number of particles, moles, get used, and then we're not going to worry about luminous intensity. So for us, these are the three major units. We are going to use kelvins once we get to the later part of the course and we're into thermodynamics. Kelvins will get used, and then in following semester we'll be using amperes. But what's funny here is that all of these other physical quantities, so you're going, well, how do we measure velocities then? Well, velocities are going to be meters per second. Well, how do we measure forces? You know, if I push on something, what are the force units? It turns out that if I take kilograms and meters and divide them by seconds squared, we're going to find out that has units of force. We'll see how this all works. So we do have other units. We have units of joules for energy. We have units of newtons for force. We have these different units, but they're all based on what I'm going to say are the fundamental three units. All of the stuff that we do that's part of mechanics within physics is based on meters, seconds, and kilograms as units. All right, now units are going to have, we're going to need to be able to do conversions between different units. And so an example of a units conversion is going to be saying that, oh, 1 inch is equal to 2.54 centimeters. So if I'm doing something in British units of inches and feet and miles, yards, and I want to convert over into the standard set of units, this is a handy one to remember, that 1 inch is exactly defined as 2.54 centimeters. Kind of interesting that inches are actually defined in terms of centimeters. Written another way, we can say that 2.54 centimeters per 1 inch is basically 1. It's like multiplying by 1. So let's say that we've done this. Let's say that we have measured something to be a length of 21.5 inches. How can we convert that to centimeters? Well, here's the 21.5 inches. And we're going to use our conversion factor. So the conversion factor says 2.54 centimeters is the same thing as 1 inch. Now, I would have preferred that they would write the 1 underneath there to be really clear. So I would have preferred this in the numerator and this written out in the denominator. In either case, what happens is the units of inches for this example are going to cancel out. If I have units of inch on top somewhere and units of inch in the denominator, the units cancel. So that's really handy, and that says now we can get out our calculator, put the numbers in, and the 21.5 inches is equal to 54.6 centimeters. So something, what's 20 inches is like that maybe? So 54.6 centimeters. All right, let's look at an example. So here's an example they have. It says that the 14 tallest mountain peaks, oh, that's pretty, in the world, on the planet, are referred to as 8,000ers because they're beyond 8,000 meters above sea level. So what would the elevation in feet be for an elevation of 8,000 meters? All right, here is our example. So I'm going to start with the 8,000 meters. Now the conversion, the only conversion I can remember is that 1 inch is exactly 2.54 centimeters. So something that's 8,000 meters, I'm going to convert the meters into centimeters first so that the meter units will cancel. Those will go away. And then I'm going to take the centimeters and use my conversion. 2.54 centimeters is 1 inch. That will make the centimeters go away. And then what I can do is I can take those inches and convert those back into feet. Now the inches will cancel out. All the units are now gone except feet. So whatever units are remaining, that's what I'm going to write down in my answer. And so even before I get a calculator out, I'm going to have feet written down on this. I'm going to go, okay, it's going to be some number of feet. And then I can get my calculator out, take the 8,000 times the 100, divide by 2.54, divide by 12, and I got 26,247. Now I'm not through, because what I have to do on every problem I do is stare at it and say, does that make sense? So what they were saying, let's go back and think about this, 8,000 meter peak. So I'm not so familiar with 8,000 meters. You know, maybe I know that Mount Everest is, what is it, 30,000 feet or something, or maybe I know that some of the tallest peaks are, you know, in that range of 25,000 to 30,000 feet. But anyway, stop and ask yourself, does that answer make sense? And, you know, given what I'm kind of familiar with mountain elevation, that would be a really tall mountain. 26,247 feet. Now, another issue we could ask about here is, if I take a look at these conversion factors, are any of those approximations, or are they exact? And in this example, the 100 centimeters per meter, that's an exact conversion. There is no uncertainty in that conversion. This is exact. This is the definition of an inch, is 2.54 centimeters, and the 12 inches in 1 foot. So these are all exact. So that raises a question of, okay, how many significant figures should we have here? Because right now I got 5 significant figures. And that would really depend on how many significant figures are we thinking are in that first number. And that's kind of a judgment call. So am I thinking exactly 8,000 meters? Because if I'm thinking exactly 8,000 meters, then I can keep however many significant figures I want over here. If I'm saying this is 8,000 plus or minus 1, then this is like 4 significant figures. And so I could keep 4, you know, maybe keep an extra one here. If that's just kind of a rough estimate, you know, saying, oh, the mountain's about 8,000 meters, how many feet would that be? Well, about 8,000 meters would be about 26,000 feet. So depending on how we're thinking about that number, that's going to determine how much rounding we want to have on the other side. All right, I'm thinking, let me see what the next example is here. Yeah, I'm thinking that's a good place to take a break. So we will have a break each day, and this is a good place to take a break. So we'll stop for a minute and then we'll come back. If you guys have any questions at all, just let me know.